Okay, so we're going to continue our kind of basic development of the notion of connectivity. So recall that a graph is connected if for any two vertices in the graph there's a walk from one vertex to the other. In the last class, we proved, for instance, that a graph is disconnected, so it's not connected, if and only if you can partition the vertices into two sets in such a way that there are no edges from with one end in one set and the other end in the other set. So there are no edges that go from left to right. So if you're disconnected, then you have such a partition, and if you're connected, then you have no such partition. Now we're going to kind of continue doing some basic development of these concepts in and around connectivity. And the first one for us today is a fairly easy proposition. This is a very routine thing, but I think it's worth just thinking about the proofs as we go along. So the setup here is I'm giving you two subgraphs of a graph. So H1 and H2 are subgraphs of a graph G. And I'm going to promise you that H1 and H2 are both connected. And they share a vertex in common. So if that's your setup, you have two subgraphs. H1 and H2 are both subgraphs of a graph G, and they are individually connected, and they overlap, and they share a vertex. Then, in fact, what's going to be true is that the union of those two subgraphs is also a connected subgraph of G. Right. I mean, I think if you're thinking for a moment about what these concepts mean, this doesn't sound particularly surprising. But it is worth thinking for a moment about how we're going to go about proving such a thing. So again, well, we will get some fancy theorems in our toolkit eventually, but we're kind of right at the start of things right now. How are you going to prove that some graph is connected? Well, what does it mean to be connected? It means that for any vertex u and for any vertex v, there exists a walk from u to v. Right? So if I need to prove that my graph is connected, the most basic thing to do is take that definition of connected. It says for every vertex u and for every vertex v, there's a walk from u to v. That's what we're going to do. We're going to take a vertex u, take a vertex v, and show that there's a walk from u to v. So our proof is going to be, we're going to let u and v be vertices of the subgraph, of the union subgraph. So these are vertices of H1 union H2. And now we're going to prove that there is a walk from u to v, right? So if we can do this, we will be showing that for an arbitrary pair of vertices in the union, there's a walk from u to v in the union. Now, ordinarily I would be pausing class to ask you how you think you're going to prove this, and I know I'm not going to get any responses, but I would sort of like to pose that question just for a moment here. I think it's good to take a moment to think, how would you prove this? So we've got a vertex u and a vertex v in the union. I know that H1 and H2 are individually connected and they overlap. How am I going to take advantage of, how are we going to leverage that information to get a walk from u to v? Well, here's the idea. We know that these two graphs overlap. There's a vertex in both of them. Let's go ahead and choose one. Oh, sorry. I'm writing some nonsense. So I know that their v of h1 and v of h2 have non-empty intersection. So I'm choosing some vertex w in both of them. So w is in both a vertex of H1 and an H2. Now, the vertex U, it's a vertex of H1 union H2, so that means it's either in H1 or it's in H2, right? So let's choose some number I, let's say equal 1 or 2, such that the vertex U is a vertex of HI. Right? I don't know if it's a vertex of H1 or if it's a vertex of H2, but it's certainly a vertex of one of the two because it's in the union. So U is a vertex in HI. Now, W is also a vertex in HI, right? W is in H1 and in H2. So the vertex U is in HI and the vertex W is in HI, and HI is connected, right? That's our other assumption. Their subgraphs H1 and H2 are both individually connected. So if I have a connected if I have some connected graph HI, I can choose a walk from one vertex to the other. So let's choose, maybe just to emphasize, I'll say, since HI is connected, we may choose a walk, say W, from the vertex U to W in HI. I will emphasize here, it is very important in these kinds of settings when you have multiple graphs at play at the same time. It's very important that you talk about which graph you're in, right? At the end of the day, I want to prove that H1 union H2 is connected. And that means that I've got to find, for any my pair of vertices, U and V, for this arbitrary pair of vertices, U and V, in this graph, I have to find a walk from U to V in that graph. Right? That's very important. Right? We're in a land where there are a lot of graphs at play. There's a big outer graph G, and everything's happening within G. I've got a subgraph H1, I've got a subgraph H2, and I know they intersect. I'm trying to prove that this third subgraph, H1 union H2, is also connected. But in order to prove that a particular subgraph is connected, I need to show that for any two vertices in that subgraph, there's a walk in that subgraph from one to the other. So it's very important that we keep clear where our walk is. Again, I guess I want to emphasize at the end of the day, the proof of this theorem is really not that difficult. I mean, I think once you sort of see it and think it through, it's very straightforward. But there really are some good points to be made just concerning how we operate in this kind of realm, how we prove these kinds of statements, and also just what you need to keep track of when you're thinking about writing down one of these arguments. And a really vital thing to keep track of is which graph you're talking about. It's just going to be a common thing for us to have more than one graph floating about, and you need to be clear what you're doing. So again, what's happening here is I have H1 and H2 are both connected subgraphs. They both share a vertex. In fact, they share the particular vertex W. We chose W to be common to the two. And I know that H1 and H2 are individually connected. Now, I've taken an arbitrary pair of vertices, U and V, from that union subgraph. U and V are both vertices of H1 union H2. And we're going to prove that there's a walk from U to V within the subgraph H1 union H2. If we can do that, we've shown it's connected. Now our first step was, well, we've got this vertex U, we've got this vertex W that's in both of them. Because U is a vertex in H1 union H2, it's either in H1 or it's in H2. So I can choose. We can just declare it's a vertex in HI for some I. So we'll let that I be our choice. And now U is a vertex in HI and W is a vertex in HI as well, right? W is in both H1 and H2. So W is also a vertex in HI. So HI is a connected subgraph. It's got a vertex U, it's got a vertex W, And that means that there's a walk W existing within HI from U to W. So we have a walk, capital W, that goes from U to W in HI. Now, similarly, I can choose a J value, either 1 or 2, such that my vertex V is in HJ. Right? I don't know if that J is going to be 1 or 2, but it's not going to matter for the purpose of this argument, right? That vertex V, it exists it's in the union, it's in V of H1 union H2. So it's a vertex of the union. That means it's either a vertex of the first one or it's a vertex of the second one. It's either a vertex in V of H1 or it's a vertex in V of H2. So I can choose a J value, J equal 1 or 2, so that V is in the graph H sub J. Now, similarly, W is going to be in H sub J. So I can now, I'm being a little pedantic. I mean, it's just because I have a teeny bit of spare space here. But since HJ is connected, we may choose a walk W prime in HJ from little w to V, right? So again, J is going to be either 1 or 2. I'm making an argument that's going to work in either case. So you can see that introducing this little dummy variable J is saving me from have to say, well, it's in H1 or it's in H2 and somehow splitting into cases. That would be annoying. I'm just going to pick J equal 1 or 2 so that vertex V is in H sub J. I know the vertex W is also in H sub J because W is in both H1 and H2. And now because the subgraph HJ is connected and both W and V are vertices of it, I can choose a walk W prime that exists in this subgraph H sub J from our little w to V. And so now I can just concatenate those two, right? So now I have a walk that goes from U to W that's in HI, and I have a walk from W to V that's in HJ. When I concatenate those two, I get a walk from U to V that lives in the subgraph H1 union H2. Now, I'll just say concatenating W and W prime gives a walk from U to V in the subgraph H1 union H2. Now, there's a sentence that sort of I just want to say here. I usually don't write. This is usually kind of taken for granted, and I'm not going to be, I'm not going to be super particular in grading your writing. I know this isn't a formal proofwriting class. I'm trying to kind of level you up. I'm going to try and do my best to sort of present proofs nicely and indicate all the right steps and say the right things. And so there's a sentence that's to be said here, and sometimes it's left implied, and that is so. I mean, you could see it. I only have room to say we're done here. So that is what I am going to say here. Why are we done? Right? Well, we have taken an arbitrary pair of vertices U and V from our subgraph H1 union H2, and we've shown that there's a walk from U to V in H1 union H2. If you wanted to be very formal and proper at this point, you would say, because U and V were arbitrary, there's a walk between any pair of vertices in H1 union H2, and therefore H1 union H2 is connected. Right? So again, to prove that a graph is connected here, to prove that some graph is connected, what we need to do is show that for any two vertices, u and v, there's a walk from u to v that's within that graph. That's what we've done here. That's what the whole structure of the argument is. We have said, well, we're going to prove the graph is connected. Let's let u be a vertex. Let's let v be a vertex, and we will construct a walk from u to v. So this is kind of the most basic, most straightforward way of proving that a graph is connected, and that's just what we've done. As I say, you don't need to write all these formalisms, but it's a thing that's worth saying here, right? So again, at the end, what have we done? Well, we've taken an arbitrary pair of vertices u and v, we found a walk from u to v, and that's what it means to be connected, and so we're done. Okay, so let's now jump to our next concept. So this, I don't know why that did that. Okay, so this proposition has primed us for our big definition here, which is that of a component. So a component of a graph G is a maximal, non-empty, connected subgraph. Oh. So I'm going to let comp of G be the number of components. Okay, so this is a definition. This guy maybe could be bolded. And that's going to be usually italics. Okay, so a component of a graph G is a maximal, non-empty. Sorry about that. A component of a graph G is a maximal, non-empty, connected subgraph of G. And comp of G is going to be the number of components. Now, there's a very important word here that is a little bit subtle, and I think it deserves some attention because it's maybe not the most familiar concept for everyone. And that's this word, maximal. Now, we're certainly well familiar with the concepts of maximum and minimum, right? If I give you a set of numbers, the maximum is the biggest number in the set, the minimum is the smallest number in the set, right? And what's going on there is that, well, the numbers are, to speak formally, numbers are totally ordered. For any two numbers I give you, one is bigger than the other, and the other one's smaller than the other one. When we work in settings that are graph theoretic, there are concepts of maximal and minimal that are, this is the thing we see everywhere in math working with sets. So it's not just here, but I'm going to say it in the graph theory setting. So this is a little bit different than the very biggest. So what's going on here? When we're operating with sets of, let's say, in fact, let me even just go with an example, just to keep things as clear as possible. Let's talk about maximal paths. So a path in G is maximal if you cannot enlarge it and still be a path. So if it cannot be enlarged. So i.e., if you added any vertex and edge to it, you would not have you would no longer have a path as a subgraph. Okay, so let's let me just draw let's draw a graph. Okay. Okay. Now, let me show you. Here is a subgraph. So there's a subgraph, and this subgraph is a maximal path. This is a maximal path. Right? Now, this is not the longest path you can find in this graph. It's very easy to make a longer one. Let me show you another one. An easier one here would be to go 9, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there is a longest possible path. This is also a maximal path. Both of these guys are maximal paths, right? Now, the bottom one, you may think of course that's maximal. You can't make a path any longer. You've found a path using every single vertex in the graph. What more could you hope for, right? Well, that is maximal. But this one above that uses only 6 vertices, that's also a maximal path in G, right? Why is it a maximal path? Well, it is a path, and you cannot enlarge it while staying a path. This is what maximal means everywhere in math, right? If I say I have a blah that is maximal, I mean I have a thing that's a blah, and you cannot enlarge it while staying a blah. Okay, so in this setting, I'm talking about paths in a graph. These two are subgraphs. They are paths. They are both maximal for the reason that you cannot enlarge them and stay within the class of paths, right? What I want are paths right now. I'm talking about maximal paths. I'm talking about paths that are as big as they can, that cannot be enlarged while staying paths. Okay, so this is the critical difference between maximal and maximum. If I said a maximum path, then I would mean the longest possible path in the graph. So maximum path is going to mean the longest possible path in the graph. A maximal path is a subgraph that is a path that cannot be enlarged while staying a path. Right? So it's not that you found the longest one. It's just that you found one that is as big as you can make it. Well, sorry. I need to speak. Let me just keep saying the word enlarged. I'm looking for synonyms here, but if you found a maximal path, you found a path that cannot be enlarged while staying a path. So the concept of minimal is similar. Let me just show you a path that's not maximal. Just to show you something else. I don't. So this is not maximal. This path is not maximal because you could add the vertex 1 and the edge between 1 and 2, and you would have a larger subgraph that's still a path. Or you could, you could add the edge from 2 to 3 and add the vertex 3 to it. So this path is not maximal. You can enlarge it while staying a path. Okay, so I have 3 subgraphs here. The one in the lower left here, that is that's actually a maximum. That's the longest possible path you can find in the graph. That one and the one above it are both maximal. You cannot enlarge either of those subgraphs while staying a path. The one on the right is not maximal. Okay, so that's just my quick primer on the concept of maximal. Minimal is the same. So if we talk about like a minimal blah, we mean that you have a blah and you cannot make it any smaller while staying a blah. And so just sort of the thing that's going on here is that when we're working with subgraphs, sometimes you don't want to, well, anyway, you don't want to throw away the subgraph you have. You just want to enlarge it as much as you possibly could. And that's what happens with this. Well, anyway, that's what brings us to this concept of maximal. Okay, I'm going to erase this. Oh, I'm going to try and erase this. Good. Okay. Okay. So, so now back to our actual definition here. So, a component of a graph G is a maximal non-empty connected subgraph. So what does it mean? It's a connected subgraph. It is it's got to be non-empty. You have to have something in it. It's not fair to just give me the null graph. And it cannot be enlarged. And now our main theorem here just says that every vertex is in a unique component. So every vertex is in one and only one component. So when I take these maximal components, they're just grabbing my graph. And this, I mean, honestly, this is, sorry, let me just draw a picture of what's going on. Of course, you know, when I'm giving you a graph, I'm never promising you ahead of time that, what I should say is, if I just hand you a graph, it might be connected, it might not be connected. Both are possible, right? If there's no explicit promise, we don't know. Maybe it's a connected graph, maybe it's not. It's perfectly possible for you to make a graph G that has here's a perfectly nice graph G. So there's a 12 vertex graph G. This graph, it has 3 components. This is a component, this is a component, this is a component, right? There are, I mean, we can tell upon inspection here, right? That first 5 vertex subgraph I've highlighted, that is a connected subgraph. You cannot enlarge it anymore while staying a connected subgraph. Same with the one in the middle, same with the one on the right. So this graph I've given you here has 3 components. So here we would write comp of G is equal to 3. Again, each of those 3 subgraphs is a connected component. What you're seeing here is that each vertex of the graph is in a unique component, and that's the statement of the theorem here. And this is kind of what it means, right? So what we're saying is anytime I give you a graph, there's going to be a partition of the vertex set, and each of those each block of that partition is going to give you a connected subgraph. So it's going to be a nice little connected subgraph you can get from any vertex to any other, and you aren't going to have any edges between the different components because that would allow you to grow those things. Right. So I mean, I think this is super easy in a sense. I mean, I think you've interacted with graphs a little bit before, likely in Macam 201, or elsewhere, this is a thing you already kind of know and feel, right? I give you a graph, if it's not connected, then it might fall apart into a few different connected pieces, but each of those connected pieces is its own little connected subgraph, and we're just getting to that notion of what those pieces are. Those are what we're formalizing as components now. But the main new thing that we're doing here is really getting our proofs rigorous and proper, right? So again, formally, a component is defined to be a maximal, non-empty connected subgraph. And what our theorem is going to tell you is that every vertex is in a unique component. So for every vertex, it's in one of these little connected pieces, one of these components. I do think this is kind of easy and intuitive. I mean, I don't think as conceptually this is particularly challenging, but I want you to take note of the proof stuff. So there's our picture. There's our graph G. This graph G has 3 connected pieces. It is 3 connected components. So comp of G is going to equal 3. And again, as you're seeing here, every vertex is in a unique component. Now, now, how are we going to prove this thing? So we need to prove that for every vertex V, it is in a unique component. So that means it has to be. So again, go back to the definition of component. So a component is a maximal, non-empty connected subgraph. So we have to show that this vertex V, it's in a unique maximal, non-empty connected subgraph. Now, how do we even know that it's in a connected subgraph? I mean, is there a danger that the vertex V is not in any connected subgraph? Like a priori, that's a possibility. Why is it the case that that the vertex V must be in a connected subgraph? Well, the easy reason here is that if you make a subgraph consisting only of the vertex V, no other vertices and no edges, well, that's a connected subgraph, right? So let's let V be a vertex, and let's note that V is in some connected subgraph. V is in a connected subgraph consisting only of that vertex V. No other vertices and no edges. Okay, so one thing's out of the way. Certainly the vertex V, it will be contained in some connected subgraph of G. Okay, so it's going to be in some connected subgraph. But how do I know that there's a unique one that's maximal? Why couldn't it be that you have a subgraph H1 that's a maximal connected subgraph containing V, and another subgraph H2 that's a maximal connected subgraph containing V? Why is that not possible? Well, maybe I've led the witness here by calling them H1 and H2. The reason is because of the proposition we proved before, right? If H1 is a connected subgraph containing V and H2 is a connected subgraph containing V, then H1 union H2 is a new connected subgraph containing V that's going to contain all of H1 and all of H2, right? So if you were to propose, hey, here's a maximal connected subgraph H1 that contains my vertex V, and here's another one, H2, that contains V, I would say, well, I'll take H1 union H2. By our previous proposition, that is a new connected subgraph. It still contains V. Assuming H1 and H2 were different, I've now constructed, I've now enlarged both of them, and therefore contradicting, and therefore contradicted the maximality. So I will just say, if H1 and H2 are components, containing V, then H1 union H2. In fact, let me maybe just for so if H1 and H2 are connected subgraphs containing V, then H1 union H2 is connected by our proposition. And this implies that there's going to be a unique maximal connected subgraph containing V. Okay, so so again, I don't think this should be scary kind of conceptually. If I give you a graph, it might not be connected. If it's not, then you're going to have your graph naturally breaks up into connected components. I think if you draw a graph, you see this immediately. Like you can just tell which of the parts are connected and which are not. So you can just tease this out initially. It's immediately apparent upon drawing the picture. But what we've done here is introduce the notion of a component, which is a maximal non-empty connected subgraph. And we have done a proper argument here. So we've leaned on that previous proposition we had to show that that every vertex is in a unique component. And again, this is kind of the picture that you're probably familiar with. Okay, so I think I'm going to end this lesson right there. We'll come back and do one more little one on connectivity.